I try the adapter to the VGA because I think something is a bit off with my. Ah, okay, it works. Just to verify.
2019. Thank you all for being here. It's very nice to see you all. And before we start the official fight, let me remind you how it started almost a week ago with this beautiful video.
It's great to see you here. I want to give you a welcome.
And the days after are also on YouTube and on Facebook. I hope you enjoyed it, guys, and I hope you'll enjoy it today as well. My name is Yevgeny Glushkov. I'm the LOC chair. I'm the chair of the local organizing committee of the IPT 2019, and I'll be with you the whole day today, and I'll make the most that you enjoy it. And today we have 3 teams in the final. Who will show you their best solutions. And the physics fight, the final physics fight, will be chaired by Yulia Zotova from MIPT and Riken. And I give you the word, and she'll do the rest.
Thank you, Evgeny, for kind introduction. And so welcome to the final fights of the 11th International Physicists Tournament. Let's start our fights from the team introduction. Team captains, please introduce your team. Please start.
Hello everyone, my name is Igor Skachina and I'm team captain of Team Ukraine, and my teammates are Oleg, Alexei, Olga, Jay and Grigory.
Thank you.
Hello everyone, we are the French team from Lyon with Lise, Pascal, Gauthier, Hector, Rémi and I, Francis, and we wish you the best for this fight.
Thank you.
So, good morning everybody. My name is Kirill Gereshnik and I'm team captain of Ecole Polytechnique, and our team goes for Anu, Tristan, Alexandre, Aris et Mathieu. Thanks for your attention.
Thank you. And now, please, let's start introductions for another important members of our fights. It's the jury members. Please introduce yourself. Let's start from this side. Thank you.
Hello, my name is Piotr. I'm the team leader of the Polish team, and I wish you good luck.
Thank you.
Hi, my name's Jess and I'm a physicist at Imperial College London.
Good morning, everybody. My name is Åke Andersson, and I have come here from the Chalmers University of Technology from Gothenburg. I'm the team leader of Sweden. I have been a participant here myself, so I know how nervous you might feel, and I wish you good luck.
Thank you.
Hello, I'm Wendy Sadler from Cardiff University. I'm a physicist and a science communicator, so I'll be looking out for some good communication. This is my first IPT event and my first time in Switzerland, so it's very exciting, and I'm really looking forward to seeing a physics fight.
Thank you.
Hello everybody, I'm Jean-Marie Fabringer. I'm teaching physics here at EPFL and I'm the team leader, I was the team leader for the Swiss team.
Thank you.
Hello everyone, my name is Suzanne Anderson. I'm the team leader for the Danish team and I've also been a participant myself and I also know how nervous you are. So I'm looking forward to seeing some interesting physics and wish you good luck.
Thank you.
Good morning, everyone. I am Luis Núñez from Universidad Industrial de Santander, Colombia. I am the team leader from this young team. Good luck for everyone.
Hello, everyone. I am Vladimir Vanovsky, Moscow Institute of Physics and Technology, Institute for Problems in Mechanics of Russian Academy of Sciences, and IOC secretary here. I am looking for really cool physics, and I hope we will see it today. Thank you.
Good morning, my name is Mark Bochkov, the team leader of Team Russia, MIPT. It was me to film you during the fights, so you will be able to work with your mistakes and improve the presentations. So let's see something even better today.
Thank you. And I will be chairman of this physics fight. My name is Yulia, and I'm a PhD student of Moscow Institute of Physics and Technology, and also in Japanese Research Institute, RIKEN. And now we are ready to start our captain's fight, and because this is a final, our captain's fight will consist of two different kind of problems. It's theoretical and experimental, and now we're ready to start from experimental problem. And in this case, to conduct this problem and this captain's fight, I would like to invite to this stage Alberto, member of ILC.
Hi everyone. So may each captain come to the floor? Okay, so each of you will be able to bring 2 team members with you, so you can already choose them. So, Julia, can you please move to the problem?
So you have 10 minutes to conduct this experiment.
Experimental fight. You have to build the longest possible bridge made out of raclette cheese, which you can cut however you want, and toothpicks. The bridge has to be built between the 2 elevated points provided by the chairman, which are in this case these tables, and it is not allowed to touch. Well, it is not allowed to touch the floor in this case because I had a different setup in mind when I thought about it. And it must hold for at least 50 seconds without collapsing after the 10 minutes have elapsed. The captains are allowed, to choose 2 team members to help them complete the task. And the length of the bridge is the distance between the elevated points. So you may go.
In this case, the time is started. Alberto, am I right?
You have 3 teams, 6 tables. Yeah, you can also change the positions of the table to make it longer. sorry, but he was different. This one was ready since Sunday. And I thought we wouldn't have theoretical ones until the last moment that we decided we want some theoretical. And he came with his, so...
The main thing is that the final, the problems were there.
Yeah. They are kept for next year, yes. I put them on the draw, I just see them.
Okay.
Because I mean, they will usually the last thing. So this one is ready for advance, that's good. C'est parti. Tu vois, yeah, 5 minutes.
J'essaie de faire une RH. C'est pas mal, hein? Là, les Ukrainiens, ils sont très forts. Alors, il y a que des cours d'ange.
Everything is closed. Oh no, actually, they don't need this.
Okay, so do you have to pay?
Yes.
Je croyais qu'on ne montrait même pas. Oui, d'ailleurs, elle a repris. Non, les points sont inscrits comme ça.
If you need some there, these are their
3 minutes left.
Think about something to forbid. They're using the toothpicks, like only and using the cheese to hold the toothpicks together instead of the other way around, which I think is a very smart idea because it should count. You agree on that? We've thought it a different way. It was supposed to be done that the toothpicks hold the cheese together, and not the other way around. Of course not. Oh, look at the other French team, what they're doing. They are super nice designs. I like those designs. J'adore les skills d'ingénierie du Polytechnique et de Metz, ils ont des super skills d'ingénierie. Je pense qu'on peut déjà leur donner un diplôme de génie civil.
1 minute left.
I remind you that the bridge must hold for at least 15 seconds after the timer has ended. At least 15 seconds. You have 20 seconds left. It's the distance between the table that counts. 10 seconds left. 9, 8, 7, 6, 5, 4, 3, 2, 1, and stop. Step away from the tables, please. Step away. And now 15 seconds have passed. So it didn't fall to the ground, so it still counts as stable. And it's long enough. And okay, well, I like those designs, to say the least. Much longer than what the IOC managed all together yesterday night to try to test the fight. So, well, let's try to measure. Can you hold me this? C'est bon, ça n'a plus besoin de tenir. Ouais, je sais, mais c'est plus beau. Je vais revenir s'il y a besoin de plus précis. Okay. So, Ecole Polytechnique managed to make 43 centimeters. Afterwards, you can go wash your hands. Not the captains, they need still to be here for the theoretical ones. So, it's fine, it doesn't, it's fine, just I remove this. It's less anyways, so. That is 33. 33, yeah. If I need more precise, I will come back. So Ukraine managed to make a bridge of 33 centimeters. And Ernest managed to make 25 and a half. It's not over yet. So that means that Ecole Polytechnique is awarded 4 points for the captain fight, and Ukraine is awarded 2 points, and Ernest 0 points. But the theoretical ones will count as half, if I am correct. So, Julia, you can.
Thank you. And now we would like to ask team captains stay on stage. Team members clean his arms or probably go to the table. I would like to ask our helper help us with clean the space. And now we are ready to start theoretical problems. And to handle it, I would like to invite to this stage Secretary of International Physicists Tournament, Vladimir Vanovsky.
One, two. Yeah, it's working. So, okay, thank you, Julia. Yeah, the experimental fight was really a nice one, and the theoretical will be more boring, but we still have to test both experimental and theoretical knowledge of the participants. So you all have got some pieces of paper, some pens, or you need one? Yeah. Okay, and we will have 3 small questions. They will be 2 points for the first place for every question, 1 point for second, and 0 for third one. For the third place of this question, the metrics will be logarithmic metric depending on to the closeness to the original answer. So let us try and go to the first question. So you will have 2 minutes to answer it. Yeah. Let us consider that LHC will be extended up to Earth diameter because they want more and more energy and money, I think. So it will be magnetic field at 11 Tesla, or what will be theoretical energy limit of accelerated protons in this case, if the diameter will be bigger.
The time is started.
Что там с временем? Тикает. Ну, потом покажешь. Подожди, дай им чуть времени. Что? Да-да-да, 4.2.0, кто 4 ЕПФЛ, потом Харьков. Сейчас сделаю табличку.
One minute left.
Yeah, the answer could be put in electron volts better, I think. But if you will put it, could you switch to condition? You have 10 seconds. Yes, you can write any units of energy you want. Okay, and back to time. The time is going out. Yeah. Okay, just give me the papers with the answers. Okay. Okay, you are from ENS and you are EPFL. So let us see the answers and let us go to the solution of this question. The solution is rather obvious. You should just consider the ultra-relativistic limit of accelerated protons, and just Lorentz force should be equal to centrifugal acceleration, considering also the relativistic gamma factor. And okay, we have 3 answers. This one is 8 to 10 to power 24 electron volts. Okay. Yeah, I see it. Then, okay, you can take your paper, I think.
Thanks.
When it's, okay, you answer. 5.2, 10 to power 14 electron volts. And, okay, you can take your paper, you'll need it. And you have 2.1 to 10 to power minus 19. It means like 1.3, 1.4 electron volts, yes? So, yeah. It's the most thorough answer, as you see, because even for the current diameter, the energy is much higher. So I think it's evident 21 to power 10 to power 15. Okay, let us see which one is closer. Look, it's the first ratio, And okay, the second one is this one is much, okay, I'm sorry, yeah. This one is much further. So we have the closest answer is the answer of ENS Lyon, I think, yeah. You have 2 points for this competition. So we have 1 point for Polytechnique and 0 points for Ukraine.
Thank you.
Thank you. Now we have 2 more problems. Let us go to the second one. Are you ready? We will have 2 minutes. I'm sorry. Here we'll carry some error in the presentation because we have timer only for 2 minutes.
Okay.
Now let us go to the question. Estimate the current going through a human body if he or she holds a naked 220 volts wire standing, and he's standing on 2 centimeter thick isolation rubber mat. Do you understand the question? The time has started, I think.
The time has started.
Better not to make experiments on this, I would advise you, because of safety concerns. Probably visualization could be not so good, or it could be wet. But so, the question is just theoretical, empirical. Переключи на условия чуть-чуть.
Up. 1 minute left.
Switch please to the timer. Switch please to the timer. Okay, you have 40 seconds. The answer should be given in some current, units. Better to be amperes, I think, but as you wish. Okay, so 5 seconds left. 4, 3, 2, 1. Just give me the papers. Yeah. Lyon is okay. It's Polytechnique. And okay. Yeah. So please switch to the official answer. Please switch to the official solution. Yeah, there is insulation mat should work somehow. So there is no point to expect some bigger currents. But we know that the current is alternating, and because it's alternating, we have some capacitance, and through this capacitance, we'll have some current flow. So ENS Lyon have given answer 20 milliamperes. Polytechnique has given answer 8 microamperes, so it's a very close answer, I think. And Ukrainian team, Kharkiv, has given answer 0.22 amperes, a very big current. I think it will kill you in a moment. So, okay, we have here a clear winner of this part. The Polytechnique has the first place, ENS has the second place, and Kharkiv the third place in this very point of the competition.
Thank you.
And now I see that the Polytechnique is out of the reach because the next question cost only 2 points. And okay, if you want, you can compete. If you want, you can just leave because it doesn't matter. Yeah, you can take your. And we have the third question, which will decide which of the teams, will have the second and the third place. Let us move to it. You will have also 2 minutes. Okay, please switch to the question. Suppose you have 4 linear polarizers, and the first and the last of them should be perpendicular to each other. And you have 2 other polarizers. You can use it as you wish. You can rotate them. And you should obtain the maximal intensity of the light going through this system compared to the initial intensity of natural light. And so we ask you to determine this ratio.
The time is started.
Yeah. Что? Да. Рев, оп. Цвет? Дополняете. Пипец, конечно. Молодцы. Я сейчас переключу часики. So 40 seconds left around it. What? You have already solution, yeah? So 20 seconds left. Polytechnique, will you give your answer or you don't need it? Okay, so we will have just 2 points and 1 point. Okay, we have all the answers. Now let us move to the solution. The solution is rather obvious. First polarizer will lose half of the intensity, and after that all the polarizers should be rotated at equal angle of 30 degrees. And the participants, have written it. But, okay, you have here the factor of 1/2 and multiplied by cosinus to power 6 of 30 degrees, because at every polarizers, the intensity is multiplied by cosinus squared, by Malus law. So we have answer, okay, 0.53 by Kharkiv team. And we have answer 1/16 by Lyon. Which one is closer? One. What? Yeah, I think also that 1/16 is somehow 3 times less than 0.21. So okay, we have Polytechnique has also already won the competition. Let us see. Okay, we have now 2 points for Ukraine, 4 points for Ukrainian team and 4 points for ENS Lyon. It's a draw, and so we need a backup question for 1 minute. Are you ready? It's just a funny one. And I will use my clock in order to measure the time. So let us start. how many Higgs bosons could be obtained after the collision of two maximally accelerated Usain Bolts if the collision energy could be fully converted into these particles? You know, the Usain Bolt, it's a very famous runner. Thirty seconds left. So 10 seconds left. 5, 4, 3, 2, 1, 0. Please switch to the solution now. What is your answer? Yeah.
We already have markers.
Okay,
No,
let us see
one.
the answer.
Only one. No. The solution is following.
What? Yeah, the solution is here. You see that, okay, we just have some values for his speed and his mass, and we just calculate the kinetic energy. The Higgs boson is a really heavy particle. So, okay, we see 7 and multiplied by 10 to power 11. Ioannis Lyon has a rather close answer, 7.8 10 to power 12. And around 10 to power 22 is answer for Kharkiv. So Ioannis is the second winner of the captain's competition. Let us applaud them. Yeah, so we have at first place Polytechnique, at second Ioannis Lyon, and at third Ukrainian team of Kharkiv. I will give the word to Julia to continue.
Thank you. And the team from Ecole Polytechnique, in which order you would like to choose right here in the table? First one, please. Thank you. And team from Ukraine, in which order? Team from Lyon? Second one, please. Thank you. And team from Ukraine? Okay, thank you for all of captains again. And in the first round of this final captain's fight and final fight, the team from Lyon will be a reporter team, team from Ukraine will be opponent team, and team from Ecole Polytechnique will be a review team. And now, Lyon team has 5 minutes for preparation, their solution.
Test, 1, 2.
One minute left.
Gauthier. Okay, so hello everyone. My name is Pascal Wang, and I represent the subject string shooter for the French team from Lyon. So a string shooter consists of a very simple setup in which a string of loop is fed between two control rotating wheels which rotate at the same speed. So you can see it live here in action or on this video in which when we turn the motors on, quite astonishingly, the loop of string rises in the air and acquires a well-defined stationary shape. It flies in the air, defying gravity. Moreover, when we tap on the string or when we blow on it, we can see waves propagating. So the question that was asked by the IPT committee was to investigate the overall shape of the loop and the propagation of waves on the string. So two parts of the question. First, we'll focus on the shape. So first, we investigate a very naive but an idea that seems very intuitive. So we collect the control parameters of the system, which are the string velocity, the string length, and the linear mass. So our very intuitive idea is that the shape of the loop is given by the competition between the inertia of the loop, which propels it forward, and gravity that wants to hold it down. So with this idea in mind, we form the dimensionless number that compares the kinetic energy of the loop and its potential energy. As you can see, the linear mass cancels out, and we are left with v squared over gl. And the purpose of the next slide is to show that this inertia gravity competition idea is too naive to describe the system. So first, a quick notation. We define the angle at the furthest point, which will allow us to compare different shapes. So it's the angle defined between the line between the vertical axis and the line that goes from between the wheels to the furthest point on the string. So we measure this angle as a function of string velocity. So for low velocities, there is the string is vertical, as if it's at rest. Then when the velocity increases, we have a transition, and the string goes from vertical to horizontal. So here we have a strong dependency on the velocity v, but here we more than double the string length. But the curves and the moment of the transition almost don't change. So the transition is controlled by the velocity, but not by v squared over gl. So this shows that there is a missing ingredient here in this our idea. But this is an experimental demonstration that the idea doesn't work. However, it was also bound to fail theoretically. We show this by doing a momentum budget on the moving piece of string on the moving coordinate, with s being the curvilinear coordinate. So we collect its acceleration, the difference of tension, and gravity on the string. Here, because the velocity is constant, we can group the v squared with the tension to build an effective tension. And so we have the same equation as a catenary with an effective tension. So the solution of a catenary is this one. And the most important part is that it only depends on geometrical conditions. So this is not believable, because this tells us that if we increase the velocity, the shape doesn't change and stays vertical, which is totally not what you have seen a few moments ago. So there is a physical ingredient missing. So it took us a while to get it, but this physical ingredient that lifts the string up in the air is drag. It's very counterintuitive, because why would drag, which is a dissipative force, lift the string up in the air? However, I will show you this clearly without any mathematical calculations. So we will show you what happens when we put our apparatus in a vacuum chamber. Here, the string is horizontal for some fixed velocity at atmospheric pressure. When we gradually pump the air out of it, the string goes from horizontal to vertical. And this is amazing because this tells us that aerodynamic forces have a clear role in this problem. What is their role exactly? Well, because of the actual symmetry of the string, there is no lift on the string. However, there is drag, which is a force that is directed tangentially at every point on the string. Because the string is a closed loop, we expect the resultant force to be close to 0. However, its net effect is that it induces a drag, a torque, directed counterclockwise, as you can easily convince yourself by following the arrows. And so there we have it. The mechanism that lifts the string is drag. Now that we understand this, we also understand the shape of the loop. So recall from the preliminary analysis that if we only consider tension and gravity as the acting forces on the string, then we get a catenary equation that does not depend on the velocity. However, if we plug in a constant drag per unit length term into the equation, now there we have the equation now depends on a dimensionless parameter d, which compares drag with weight. So there we have it. This is the parameter that we were looking for, the one that controls the system and gives the system its shape. So now that we have this equation, we can make predictions. So this is a photo of a string of loop, and by finding the right parameter d, then we fit the shape perfectly. So a model is valid for this shape, but it also reproduces the shapes of the loop from vertical to horizontal. And as you can see, when we increase the velocity, the parameter d increases. So we measured d as a function of v to see what is the dependency, which gives us this graph, so d as a function of v squared. So we can see there is a quadratic dependence of d as a function of the velocity, which is coherent because the Reynolds number in a problem when the string begins to rise is of 1,000. So this means that that the drag force is quadratic in the velocity, which is exactly what we retrieve experimentally here. So this concludes our analysis of the loop, of the shape of the loop. I hope I've convinced you that the driving mechanism of the problem of the system is drag, because it creates a torque against weight. So the parameter of the problem is a dimensionless drag, then compares drag with weight. We derive an equation of the shape, and it allows us to make predictions. So now that we understand the shape, we move on to the second part of the question, which is wave propagation. So here on this video, we tap on the top of the loop to create a large amplitude wave for clarity. So tapping at the top, here we can see a wave at the top, but also quite surprisingly, a wave at the bottom. These two waves travel to the tip and slow down as they go to the tip and die out. Moreover, the top wave propagates downstream, so same direction as the string, whereas the bottom wave goes upstream, so in the opposite direction. We will explain these three observations. So first, recall that for a string at rest, if you excite it somewhere on the string, then you expect one wave to the left and one wave to the right, with velocities given by the tension and the linear mass. And this changes a bit when the string is moving. So to get the apparent velocity, you have to add the velocity of the string. So this leads to a slow wave, minus sign, and a fast wave, plus sign. So the slow wave you have already seen on the video before, and now I will show you the fast wave. On this video, we film the string transversely, and we blow on the top part of the string to create a wave. So here, the fast wave is in red. You can see that the whole loop shifted to the right of the frame almost instantaneously, but it was not instantaneous. It went at the speed of the fast wave, which reflects on the wheels and gives birth to the bottom wave. So the bottom wave is actually a reflection of the fast wave between the wheels. So now that we understand this first observation, we move on to the second one. The slow waves slow down and die as they reach the tip. So this is clear in this video. The velocity goes to 0 as it approaches the tip. How can we understand this? Well, we use our momentum equation that we derived. So this gives us a tension profile in the string, which is simply a constant, mu v squared, plus a term that depends on the location on the string. We simply evaluate this expression when the string is vertical. So phi, the angle between the tangent vector and the vertical axis, is 0. So this gives that the tension is simply mu v squared, which can be seen as a kinetic tension. Now we use velocity addition, and we combine the two, and we get that the apparent velocity of the wave is 0. So this explains why the slow waves die when a string is vertical. But how exactly do they die, and how exactly do they slow down? Well, let's consider a limit case. So for just a hanging rope, the tension is 0 at the bottom and maximum at the top. And because there is a constant linear force acting on the rope, so gravity, the tension is a linear profile with slope mu g. For a friction-dominated string shooter, so when gravity is negligible compared to the drag, it's the same situation. You have a constant force per unit length. So the tension is maximum at B, minimum at A, and the slope this time is not mu g, but it's the drag force. So recall that at the tip, the tension is mu v squared, which gives a scaling of t minus mu v squared as a function of the difference of location at the tip. We use the same equation which we plug into the velocity addition, which gives us that the velocity of the wave is proportional to the difference of location of the tip. You recognize an exponential relaxation of both the position of the wave and its velocity. So here, this is exactly what we achieve experimentally. Here we track the position of the wave. We plot it in semi-logarithm scale. We can see a linear fit, which indicates clearly that there is an exponential relaxation of the velocity and the position. Third, we explain why there are slow waves at the top, where the top waves are downstream and where the waves at the bottom are upstream. We use exactly the same ingredients, namely the tension profile and velocity addition. This time we evaluate them at the top. The tension is less than mu v squared, and the apparent velocity of the waves is positive. So the waves at the top are downstream, whereas at the bottom, where it's similar, the tension is more than mu v squared this time. So the waves at the bottom are upstream. So this explains the third observation, the different propagation of waves is due to the tension profile. So to conclude, we showed that the driving mechanism is drag, the one that creates torque and elevates the string in the air, which is very counterintuitive. We found the right parameter of the problem, which is the one that compares the drag force with gravity. We have an equation, we derived an equation and are able to predict the stationary shape very accurately. And so wave propagation, we understood why there were two waves, two different directions of propagation, and we showed analytically why there was an exponential relaxation of the speed of the slow waves when they go to the tip. Thank you for your attention.
Thank you. And now we have time for clarification questions from the opponent team from Ukraine. Please use microphone.
You said that you neglect elasticity for ropes that you used. For which ropes the elasticity may play a role?
If you use rubber bands, then obviously it would play a role. But the rope we used, if we suspend 1 kilogram, then you will see no elasticity.
Also, in your theoretical plots, there are for example, for this one, at the point with the maximal deflection, there are strong change of the tangential of the rope. How can you explain this?
Can you repeat, please?
The tangent strongly changes at this point.
Okay. We didn't explain this in the presentation, but we have to solve this equation separately the top and bottom part because of a numerical singularity.
Okay. And also, have you tried to vary the thickness of a rope or of its material?
Yes, we changed the linear mass of the rope. It gives us the linear mass matters.
Okay.
Do you want me to explain the plot, or it's okay?
Okay, thank you.
Do you consider that the drag coefficient around the rope changes with the position and the velocity of the rope with the coordinate?
No, it doesn't. No, it doesn't change. This is what the plot So we plotted d as a function of v squared, and because there is a constant slope, then the drag coefficient is constant.
Okay, and also to solve numerically for the shape of the loop, were the initial conditions on the angle at the wheels?
The initial condition is always a horizontal loop, in our presentation we only show horizontal loops.
Okay, thank you.
Thank you for questions. And now the opponent team have 3 minutes for preparation.